Hi everyone, I'm Gillblad. I'm at Chalmers, where I'm leading the Chalmers AI Research Center, and I'm also part-time at AI Sweden, where I look into more of the technical aspects of AI for Swedish society and looking for forward directions on how we develop it on a societal scale. So, in the theme of today, software powering the digital future, I'm going to talk a little bit about software for AI and how perhaps we can even increase our incorporation of software engineering and true engineering practices when we develop artificial intelligence applications. So let me start very, very briefly with a question that I realized a few weeks ago that I still do get. For 20 years, I've been working with machine learning and artificial intelligence, and perhaps still the most common practical question that I actually get is, how much data do I need? And of course, there is no real fixed answer to that. It depends so much on the application, so much on the robustness of the model that you want to create, what kind of data that you can actually get hold of, etc., etc., etc. But it's a super fundamental question to AI and machine learning. And if you listened to me talk before, you've probably seen this slide. It's a number of fundamental things for AI that we're working on within research, but perhaps we have not got all the solutions so far, and perhaps we will never really get all the way for all kinds of models and applications. So what I was talking about, how much data do you need, really relates to the fundamental limits of learning. How much can we learn from a limited data set, and how do we actually answer in a new situation how much data we need? Well, how do we work around these issues? Well, basically, at least as far as I've been involved in earlier application development, we do this by relatively careful engineering. We look at the data, we work iteratively to come up with solutions that seem to test well and work in practice. And the same thing goes for many of these fundamental issues. Robustness can be sort of created by carefully selecting your validation datasets, developing them over time, and continuing to measure the performance of your models, etc., etc., etc. If you want explainable models, quite often it's actually somewhat doable to engineer your way around simple black box solutions by picking them apart, making things explainable that do need to be explainable, and making things traceable in a larger machine learning or AI system. So we already do work with very careful engineering of AI applications in practice. So how do we develop this? Well, first let's take a look at how we actually develop real applications today. It's a rather incremental data-driven approach. What is the problem? What data do we have? What data can we get? And then iterate from that. And it's quite often the case that it's better to, instead of developing new models and approaches and stuff like that, we look at new sources of data, refine the data, and so on. So we work a lot with engineering our data. Here we're talking about engineering as well, basically. And there are lots of ways of working with this. They've been around as long as I've been working practically with these kinds of problems. There have been models for handling this kind of process. They're still valid. They're still useful within data mining, within model deployment, and so on. But so far, I do think they're still a little bit limited in what we actually try to do in the real world and with the paradigms for AI and machine learning that are coming up. So perhaps we can fuse a little bit of software engineering, a little bit of knowledge from other applications with practical AI engineering development here to create new opportunities for research and accelerating product development. Because sometimes you need to move a little bit beyond this kind of batch and table model where you say that you have a data set, you're looking at it, then you develop a model and then you deploy it. in practice, quite often the representation changes a lot during development, of course. Data comes and goes, semantics of data change over time, and so on. And all this must be managed by model, benchmark, feature management systems that continuously need to adapt. So it's quite complex system that we're building of many, many, many components that need to work together. So part of this is a direction that I think will become more important in the future. That is, we often talk about AI and machine learning as a quick fix. It's not necessarily always the case. Sometimes you actually don't have the data to start with, you don't have the systems to start with, etc., etc. You need to start slow. You need to start to think about this as a system that develops over time, that will take years to fully mature and actually work. And this is something that, in combination with another development, that we're sort of at least moving a little bit beyond end-to-end models and just solving, for example, singular machine learning problems one by one, but actually reusing language models, vision models, combinations of these models, putting them together in relatively complex systems to solve way more complicated tasks than we did before. All of a sudden, with a system that develops over time, that comprises many, many components, some of them pre-trained, perhaps updated, and so on, we have a lot more engineering issues at hand. So the traditional data science, is that a sort of dying kind of work? No, not necessarily, but it really needs to be incorporated into AI as a full engineering problem. I do think it's very difficult to look at just modeling as a very, very singular part of the problem and not incorporating that with how to manage a fully running system in the future. So if we use AI engineering as a starting point, if we base our work on how real applications are developed and deployed, perhaps we can actually find really, really good focus areas for our AI and machine learning research as well to solve exactly these kinds of questions. Because the future of AI is definitely more general systems. Generalization and robustness means everything. That's what's going to change real applicability of AI. And we've seen super big capacities and spectacular demos, but they're still going to require quite a lot of engineering to work in practice. If we are going to be a little bit speculative, perhaps we can even think about approaching AI, a more general AI, as an engineering problem itself. We have components where we can take from cognitive science, from biology, etc., that probably at least gives us a direction of where to compartmentalize the problem and how to start working on this as an engineering project in itself. That would be extremely fun to do, basically. So how do we actually then approach this as a research problem? Well, probably mostly like a challenge. Let's try to build bigger systems with all components necessary with an eye to actually deploying it and running it in real life. And to do that, we do need to take a practical engineering approach to develop these AI methods. We can perhaps see more general AI as an engineering problem. I would really like to try that out. And I really do think that we can build on existing software engineering approaches. And finally, if we want to do this, let us use real-world challenges to provide scope. Otherwise, I think it will be super difficult to know exactly where to look for problems, challenges, and verification and validation. So with that, I would like to thank you for the attention. Thank you for having me. If you would like to discuss any of these issues further, please feel free to reach out.